Welcome to my Physics 2211 Lab Report 2, Motion of a Falling Object. So first, this is a table of contents going over what we'll be talking about today. What's the purpose of this lab? The purpose of this lab is to fulfill the following. Create an experimental model wherein an object is falling straight down, and create two corresponding computational models to compare results, one with drag and one without. These, when accomplished, will demonstrate the following physics principles: Newton's second law of motion, force of gravity and drag force, and velocity update formula. So, this is Newton's second law, the momentum principle. So Newton's second law states that F net is equal to the change in momentum over the change in time. We went over this in Lab Report 1. So ultimately, if you divide both sides by mass, you can get the velocity update formula, which is v final equals v initial plus acceleration times time. And that will be relevant going into the creation of computational models. So some new concepts for this lab report are the forces of gravity and drag. Lab Report 1 dealt with horizontal movement, and this one deals with vertical movement. So there are some new forces there. So gravitational force generally is equal to gravitational constant multiplied by the mass of a system and the mass of the object exerting gravity over the system. And that's over the magnitude of their distance squared multiplied by the unit vector for the distance between them. So on Earth, that translates to the gravitation constant multiplied by the mass of Earth multiplied by the mass of the object over the radius of Earth squared, where we assume that the distance between Earth's surface and the object is negligible. And that's multiplied by the vector dealing only with vertical movement, which would be 0, 1, 0, because there's only movement in the y-axis. And so if we multiply all that out, we get 0, negative mg, 0 as gravity's effect on objects. And then the force of drag is the negative proportionality constant multiplied by velocity squared multiplied by the unit vector for vertical movement, which is once again 0, 1, 0. So that leads us to have F net with drag being equal to force of gravity plus force of drag, which is equal to negative mg plus bv squared. And those are allowed to be added together because they both only affect the y-axis if you're dropping something straight down. And so that means they're both being multiplied by 0, 1, 0. So that's what v hat is over there on the right. For system and surroundings, my chosen system was a crumpled piece of paper. The surroundings were everything around the ball, including Earth, and the air making contact with the paper as it fell. And the air is what ultimately generates drag force. And a preview of findings is that the computational model accounting for both gravity and drag was more consistent with the experimental model than the model accounting solely for gravity. For experimental design, I recorded a video of a paper ball falling straight down with an object in the background for measurement. In my case, I used a 36-inch TV because I didn't have a measurement tool on me. I didn't have a ruler or anything. But that came out to be 0.914 meters, and that's what I used for calibration. And then I used Tracker to plot a position versus time graph to observe changes in y over time. And I established initial conditions to use in computational models, which will be presented on the next slide. These are the initial conditions. So initial position was 0, negative 0.0040 meters. And initial velocity, since the paper ball was stationary, is just straight zeros. Then acceleration from gravity, as explained earlier, is 0, negative 9.80. In this case, mass isn't factored in because we're not dealing with force, we're just dealing with acceleration. And then proportionality constant b was derived via trial and error, and I found that to be 0.925 in my case. So for the gravity-only model, you can see b equals 0 because there's no drag. And so for F net, I don't factor in drag at all. It's just negative mg, which is gravity. And then for gravity and drag model, we can see my derived b value. And then we can see that the F net in the y direction is negative mg plus b times v squared. So that's consistent with the formula we presented on this slide. So for some data analysis, this is the graph that I generated. And so as you can see, it shows that with gravity only, then velocity appears to be increasing much faster, which is causing the change in the y position to increase by much more as more time passes. Whereas the gravity plus drag model is much closer to the experimental model, which means it's a better predictor of real forces on Earth. So similarities between the models, both computational models and the experimental model depicted the change in position increasing in magnitude between each step of time, indicating increased velocity. This is consistent with Newton's second law and velocity update, as the effects of gravity are changing the net forces on the paper ball and causing it to increase in downward velocity over time. Now, this is also represented in velocity update because acceleration is negative 9.8, and that's causing v final to be greater in magnitude than v initial. So for some differences, the computational model accounting only for gravity shows a much starker increase in downward velocity over time, as it does not include the oppositional force of drag. The gravity plus drag model, on the other hand, includes oppositional force to gravity and is thus a much more accurate predictor of true downward velocity, as indicated by its similarity to the experimental model. Now, some possible sources of error are that point masses were not in the exact middle of the ball every time. I'm not perfect. I could have made some tracking errors. And then there also could have been horizontal movement in addition to vertical movement, which would confound F net calculations a little bit. Our what-if question for this lab is which models, if any, predict a terminal velocity. So in this case, no model predicts a terminal velocity, as velocity is increasing at t equals 0.6, which is the final time step in all three of my models. Terminal velocity is achieved when the change in velocity in the y direction is equal to 0, and that doesn't occur here. Now, if we drop the paper ball from higher, or we had way more timestamps, it's possible terminal velocity would be hit, but in this case, there's just not enough time for it to hit, and there's not enough vertical distance for it to travel to reach terminal velocity. So the other what-if question was terminal velocity happens when the force of drag pointing up has exactly balanced the force of gravity pointing down. What does this mean for net force? So if force pointing up and force pointing down are equal to 0, are equal to each other, then that means F net is equal to 0, because force of gravity is equal to negative force of drag, so F net equals Fg plus Fd would be 0. And then our what does it mean question is, imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? So if the object was initially thrown downward, this would make the downward velocity greater at the beginning of the velocity versus time graph. Because drag force increases in magnitude with increasing velocity, the force of gravity would equal the negative force of drag sooner, which means terminal velocity would still be the same value, but it would be reached faster in the case of an object being thrown down. Thank you, and I hope you learned a little bit about physics.